Okay, in this video we're going to take a look at exponential functions and then do an example, and then look at the number e and what that looks like. So first of all, basic definition of an exponential function, basic form of an exponential function is just a to the x, so that's some number to the x. So for example, y is equal to 3 to the x, that's an exponential function. Y is equal to 3 to the x minus 1, that's an exponential function. The main idea behind an exponential function is that the variable is in the exponent. Okay, that's what you're looking for. Not x to the 3x, something like that. But the variable's in the exponent. Okay, here it says graph the function and state its domain and range. So first of all, on your graphing calculator, go ahead and graph it. And then come back here. And when we graph this thing, you notice that it's just the function 3 to the e to the x, but moved up 3's. Something like this. Okay? So it's going to go something like that. And so then your domain is going to be all real, so it can be any possible x value. And then your range, okay, you notice there's a horizontal asymptote here at 3. Okay, so it's not inclusive of 3, that's why we use a parentheses, not a bracket. And so your range, it goes the lowest y value to the highest y value to infinity. And then that's your range. Okay, and so again, they're not inclusive. And another way to write this remember is that y is greater than or equal to.
What is this for?
Y is greater than, sorry, not greater than or equal to, but just greater than 3, and then x can be anything. So x would be from negative infinity to positive infinity. Okay, let's do another example. Looking at this example, it says use the graph to find the zeros of the function. Go ahead and graph that and try to find the zeros. That's where it crosses your x-axis. When you think about the graph and what it looks like, it's going to have your horizontal asymptote down here at -4, then go up sharply like that. And you notice that it crosses between 1 and 2, and so then your 0 is at x equals 1.386. So with exponential functions, you just have to be familiar with what they look like. And be able to sketch a graph of the general parent functions, and especially e. We do in calculus, since a lot of what we do is applied, we use e a lot, so just be familiar with what the graph of e looks like and how to move it around on the coordinate plane. Different rules for exponents. I'm not going to really go over these, except number 4, there should be an equal sign right there. They're here for you. We've done them before. You started using them in Algebra 1, maybe even pre-algebra, the different rules, especially with logarithms, since exponents are, in fact, different ways to write logs, and logs are different ways to write exponents. It's pretty important that you understand what these rules are. And then also, another way that we're going to apply exponents is by showing growth and decay. That includes half-life, stuff like that we'll get into later, but y is equal to some constant times a to the x. That's your basic growth decay model. And if a is greater than 1, okay, so in a sense that represents, so if a is greater than 1, then that makes it a growth problem. If a is less than 1, then that represents a decay. So a, the variable a, Okay, in a sense, it tells you what's left after a certain amount of time. So if A is greater than 1, that means more than 100% is left. Okay, after a given amount of time, if A is less than 1, that means that, let's say, 80% or 0.8 is left. And then 0.8 again, then 0.8 again, and so that's decreasing. So A tells you what's left after a given amount of time. So in a way, you can say it's a rate as well. So let's look at an example that kind of applies what an exponential growth model is going to look like. So on this one, it's a population of Virginia in the thousands. So in 1998 to 1990 or 2003, you have those amounts. So compute the ratios of the population in year 1 by the population of the previous year. So what you're going to do there is looking at the ratios, and it says the population in the previous year, so population year 1 by the population per. So you're going to compare, for example, this ratio. So you would have 7,000. Then the previous year is 6,901. And then that ratio is 1.0143. And then you would do this, so that'd be 7,078 over 7,000. And then that ratio is 1.0111. Okay, so from the first year to the second year is 1.0143, and then second to the third, and so forth. Okay, so then go ahead and write those down. So we have the first two. Go ahead and write down the other ones. So here we have all of our ratios. The first, second, third, fourth, fifth. There's a total of 5 possible ratios. The last one is the 7386 to the 7288. And then it says, based on part A, create an exponential model for this. Ours might look a little different. Okay, if you go through, you want to average these rates. So add them all up, divide by 1, 2, 3, 4, 5. You should get something around approximately 1.013. Okay, so on average, this is the rate. And you notice there's not like a real big jump from one year to the other. So on average, that's the rate of increase. And so your model, exponential model, is going to be y is equal to, we have to start here. So that'd be 6,901. Okay, so that's 6,901,000. So you would throw a couple zeros on there. And then times, it's increasing, so it's a population growth of 1.013 to the n. Okay, so this is where we start in this case, since we don't technically start at 0 population or 1 population or whatever. And then C, use your model in part B to predict the population of Virginia in 2008. Okay, so the population of Virginia in 2008, so that's going to be, 10 years after we started this model. And so we would take 6,901, and N is your years after 1998. So 6,901, 1.013 to the 10th. And when you plug that in, and then times 1,000, because you get 7852.4735, but that is in thousands. So it's 7,852,473 people in 2008. That's what we can assume the population is going to be. And then lastly, let's just take a look at the number E. The number E is really interesting because it is the natural, in a sense, it is the natural logarithm because remember, e is just log base e. Okay, and then that equals, the natural log of x. Okay, now where does this number e come from? Because it's used in history, in science, in art, by ancient civilizations, and it's used in beauty. The closer one's ratios are to e, like the distance from the center of your face to your eyes, where your nose is, whatever, all of these things, plants, animals, architecture, the closer their ratios are to e, the more beautiful, more aesthetically pleasing it is to our eyes for whatever reason. Anyway, e comes from this. Here you have the compound interest formula. And what if you compound it continuously? So not 10 times a year, not 20 times a year, not 30 times a year, but an infinite amount of times per year. And so as x approaches infinity, all right, so it would be the limit as x approaches infinity of 1 plus 1 over infinity to the infinity. That's basically what we know as e. Okay, so when you're compounding continuously, which is always used in application problem when it comes to nature, things growing or decaying, you're going to use this formula, the PERT formula. Okay, that's your growth decay model that we kind of looked at earlier, where R is your rate, T is your time, P is your principal or beginning amount, Y is your end amount. So it says determine how much time is required for an investment to double, that's the key word, in value if the interest is earned at a rate of 5.75% compounded continuously. So you notice it sounds like there's not enough information, but there is, because all they do is tell you to double. You can put in $1, you can put in $1,000, $1 million, $200 million, doesn't matter. So your end amount is 2, your beginning amount is 1. Okay, so it's going to look something like this. And they also give us our rate, and they want to know the time. So it's just going to be e to the 5.75, so 0.0575 t. Solve for t. So you're going to do the natural log of each side, or log, it doesn't matter. You'll get the same answer. So natural log of 2. Okay, it would have to be, you'd have to do the log base e of each side, I guess. So this e would cancel out, and log base e of e is 1. And then you would have 0.0575 t left over. Divide that by the natural log of 2. So it would be natural log of 2 over the 0.0575. And that's your t. And when you plug that into a calculator, you get about 12.054 years. So about 12 years. You know, and that's doubling any amount. That doubles $1, that doubles $100 million. It's going to take 12 years. That's it. Okay, so we reviewed exponential functions. Be familiar with what their graph looks like, how they're used, how they're applied, and then also remember with our application problem, what that looks like and how to take data and convert that to an equation or formula or model that represents that data in terms of the exponential growth. And then again, most importantly out of all this, the number e, and that's what we're going to mostly focus on in terms of calculus application problems.